that's obvious, please just stop me. All right, part B. What did part B say? Part B said, find S of 2. So that's just saying, hey, look, now that you have the position function, you can actually find where this object was at any point in time, right? So what was it at 2? Where was it at 2? So that just means plug in 2 for all these t's. And that is, let's see, 8 times 4, right? 32. 4 times 3 minus 12 plus 10 plus 1, I think. 31? Mm-hmm. For some reason that just doesn't look right, but 31. And that would be maybe 31 feet, 31 miles, 31 meters, whatever the units are in the problem. Okay, 4 o'clock, y'all good? And we have some more examples to do here with this, but I think this is a good time for me to show you something that I find really kind of amazing. And if I did this in the Cal 1 class, if y'all remember this, I'm sorry to make you sit through this again, but I think it's worth showing. Any of you that have taken like a physics class? Anyone? Maybe you're in a physics class right now. Do you recognize this formula? Some version of this formula. Let me put it up here. And this was actually in college algebra too. D of t equals negative 16 t squared plus v naught t plus d naught. Something like that. Show of hands. Okay. This is a formula that you can use on planet Earth. And what it does is it will tell you the position of an object that you drop and just let gravity take over. All right? That's the formula. So what is V naught in the problem? V naught is what we call the initial speed of the object. So the idea is this. If I take an object on Earth and I drop it, right, then I should be able to predict where it's going to be at every point in time. Because all objects on Earth fall at the same rate, regardless of their weight. I hope that you've learned that much. Doesn't matter how much something weighs, they will fall at the same rate, as long as you do what? You have to neglect one thing, and it's a huge thing, air resistance, right? If you take air out of the equation, then all things will fall at the same rate. And this is the formula that we use for that. So I realize this is without air, and I realize that's not a good model then, because we have air. But you got to start baby steps, right? You get into physics class, you learn about free body diagrams, and you don't talk about friction to start, and then you bring friction in later. Well, we don't let air be there. The formula is pretty clean. Later on, we let air be there, right? So this is the initial speed, and then d naught is the initial height of the object. All right? Yes? Where did that formula come from? Chapter 7? Yeah, exactly, right? What's that? So what about that? Say it again.
It's based off like it's an antiderivative of objects in free fall.
What did I just do?
-16 comes from.
Okay, yeah. Let's think about this. When you let an object go, right? When you let an object go on Earth, there's only one force acting on it, right? And that's gravity. And gravity is an acceleration, right? You have an acceleration there. And we're able to measure that acceleration. Does anyone know what the acceleration of gravity is? Negative 9.8 meters per second squared, which really means meters per second per second. However you want to write that, I don't care. That's negative 9.8 meters per second. Per second. Does anybody know what negative 9.8 meters per second squared is converted to feet per second? Go ahead, get your phone out. Whoever has their phone readily available. Convert over, go 9.8 meters to feet. Google does that.
32 feet, 1.827 inches.
32 what?
32 feet,
Mm-hmm.
and then 1.827 inches.
Okay, so we're going to actually round here, all right? It's about 32 feet per second, because 9.8 is rounded too. This is not perfect, all right? There's some error in this. So that's about 32 feet per second, right? You with me? Okay. And the acceleration of gravity, we look at it as being negative because it's down, and if it was going up, it would be positive. So here's what I'm telling you. If I tell you right now that if you drop an object on Earth, that it has a constant acceleration, doesn't it? No matter what the time is, that's your acceleration on Earth for an object that's been dropped. Okay, what's the velocity at any point in time? Well, integrate it. Antiderivative. What's the antiderivative of that? Negative 32t plus some constant. All right? Now, I can't tell you which part of the family, right, this function comes from. But what I can tell you, you would have to give me some condition, wouldn't you? You have to give me some information about v for me to nail down that c. That's fine. I'm just going to stop. What I'm going to notice, though, is this. What if v was 0? What if v was 0? What would this turn out to be?
Constant.
Just the c, right? So that c is the actual speed at the beginning, isn't it? Mm-hmm. So why don't I, instead of calling it c, why don't I call it v naught, and everyone understands that's my initial speed. That's the speed at the beginning. With me? Yeah? Okay, so I'm going to erase that and put v naught. That's just a constant. I don't know what it is. Now get the position. What's the position? I'm going to call it d of t instead of s of t. So what's the antiderivative of negative 32t? Negative 16t squared. Plus, what's the antiderivative of v naught? V naught t. Right? Plus some other constant d. Yeah? I don't know what d is, but I didn't know what v naught was either. And let's think now about this d. What if you plug 0 in for this? Gone, gone, and all you get is d, right? So isn't that the position of the object at the beginning? So I'll call it d naught.
So you have two different positions at the beginning? Is it v naught at the beginning?
No, when you look at this formula in physics, if you want to use this formula, you need two pieces of information. You need to know where the object was at the beginning, how high off the ground it was when you dropped it, and you need to know if there was initial speed. So initial speed means this. If you just drop it, your initial speed is 0. If you throw it down, you've given it some speed, so this will be a positive number. And then if your initial speed, if you're going to let it go, but you kind of throw it up first, then your initial speed, sorry, that's positive, that's negative, sorry. All right, so if you know those two things, where'd that other one go? Oh, there it is, okay. If you know those two things, then you can tell me exactly where it is at every point in time. What I'm getting at, though, what I think is amazing about this is what's the only thing we really needed to know in order to recover the position of something? Gravity. We only needed to know the acceleration of gravity. That's it. So this formula should work everywhere, right? This should work on the moon. This should work on any planet that we can stand on and survive on, right? We should be able to predict these things. All we need to know is the acceleration of gravity right here. Well, I erased it, never mind. All right, so I think that's pretty cool.
Don't we still need to know, like, v naught and d naught?
What's that?
Don't we still need v naught?
Yes, but you would have to know that. That would have to be given in the problem. So I can't talk about where something is at a point in time unless I know, like, where it started at, right? But everything else, once I know that, I've got it all, right? Okay.
So a big part of it was moving from meters to feet. Could you have just stuck with meters?
You could have just stuck with meters, yep.
It would
Yep.
have been a small one.
Then your S of t would have been, your S of t would have been, you know, at a certain point in time, after 5 seconds, you would be 4 meters instead of feet. That's it, though. Just when you're usually introduced to that formula in like a physics class or even in college algebra, they tell you everything's measured in feet and seconds. But when you get to like physics, they usually do acceleration of gravity in meters per second. So, yeah. All right. What happened to my notes? They disappear. I guess we're done. Okay, so this is the official homework assignment for this section. But I wanted to do one more type of problem before I push you into that and before we get into 5.5. This is a problem that may come up in your homework and you may see on a test. So let's take a look. What if we have something like this? A of t equals, I'm going to make this up, which means that the numbers are going to be a mess, all right? And we just need to be prepared for it. I'll try and make it somewhat clean, though. 12t minus 8 let's make that t squared and make that 8t and then make that plus 1. Sorry. And so this is an acceleration function, right? And I'm going to tell you this. S of 1 is 10 and S of 2 is 4. Find S of t. Good. I was just about to ask you, do you notice anything different about this problem compared to the others? And yes, that's exactly the issue. I have not given you any information about the velocity function. So if you think about this graphically, you start with your acceleration function. We try and go backwards to velocity, and we're never going to be able to nail this one down, are we? And how are we going to get back to the position? And it turns out we still can, all right? We still can, but let's just see where the algebra takes us, all right? All right, so let's start out. I think we can get the velocity. V of t is going to be 4t cubed minus 4t squared plus t plus c. Agree? Y'all all agree with that? I'm really kind of cranking through these antiderivatives, but please understand, I would expect that if this is your first time seeing it, that you're not just like spitting that out. You're actually going through and doing all the work for them, right? Okay, so you've got this, but you don't know what C is. And you're never going to get C because you don't know anything about V. All right, big deal. Let's just do the antiderivative again. So the position would be, what's the antiderivative of 4t cubed? T to the 4th. See, I kind of made it nice there. T to the 4th, and this one, minus 4/3 t cubed. So again, I'm doing the power rule on each of these. What about antiderivative of t? 1/2 t squared. And then what's the antiderivative of c? CT. But I also always need to put a constant in because I did the antiderivative, right? So plus d. And this is another reason why I said don't use c twice, because if you get a problem like this, you need 2 letters.
So now do we fill it in each one?
Now let's use the information we have, right? I want to know what? At this point, I need to find C and D, right? Both? C and D? Both of them. But I have two pieces of information. First of all, I have S of 1 is 10. So that means if I plug in 1 for all my t's, it should spit out 10, shouldn't it? So let me do that. What if I plug in 1 right here? What do I get? 1 minus 1 right here, so 4/3, and then 1 right here, plus a half, and then 1 right here, plus c, and then nothing here, plus d, and then that needs to equal what? 10. And we can put all of these together, can't we, into a nice number? Let's see if we can do that. I'll take anyone's answer when they have it. A sixth, is that what I heard? 1/6? Okay, we have agreement. I'm going to go completely based on your results. I'm not even thinking about the problem. Yes, 1/6? We have multiple 1/6, so we're going to trust that. All right. Plus c plus d equals 10. And I'm realizing right now I'm never going to be able to solve this for c or d because I have two unknowns in one equation, so I can't figure it out. But this was only the first piece of information. When I do the second piece of information, I'm going to have another one of these equations, right? Yeah, I'm going to have a system of equations. I'm going to have two equations and two unknowns. And then I'm going to go back to college algebra. How do we solve systems of equations? Yeah, so let's just keep going. But I want to keep cleaning this up. I'm going to subtract 1/6 on both sides. So what's 10 take away a sixth?
59 over 60.
What is it?
59 over 60.
15, is it?
59 over 6.
59 over 6.
What is it?
60?
Oh, no.
I think you said 60. I heard 60.
I think that's 60, right?
All right, 59 over 6. So all I did was subtract, well, I didn't do anything. Subtract 1/6 on both sides. All right, so I'm going to box this up, just so we remember it's there. Now, the other piece of information we have is that S of 2 is 4. So I'm going to put, I don't want to erase this because I'm going to use it. So I'm going to erase these. I'm going to keep this one here. I'm going to put here, but also S of 2 is 4. And this one is going to be a little interesting. So plug 2 in here. What's 2 to the 4th? 16. Minus, okay, 2 cubed is 8. 8 times 4 is 32. 32 over 3. So I have 32/3. Okay. 2 in here, 8. 8 times that, 32/3. Okay. 2 in here.
Just 2.
4, and then half of that's 2. So we get plus 2. And then c times 2, so plus, I'll put 2c, and then plus d. And what does this need to be? 4. And again, I can put these together. You might want to do 16 plus 2 first, because that's easier, right? 18. So I'm doing 18 minus 32/3. You could even move them both to the other side right now.
Wait, what time were we using?
What?
What time were we
I was using this one, 2, plugging in 2 and spitting out 4. So I think I did this. 2 to the 4th power 16.
Oh, okay.
2 cubed 8. 8 times 4, 32 over 3. 2 to the 2nd is 4 times a half is 2. And then 2, yeah. All right. I need to move down here with this whole thing. I've got 2c plus d equals 4 minus 18 plus 32 over 3. I decided to move these to the other side before I do any fractions because I can put these two together. Just trying to, I'm like holding off on having to do fractions here. 2c plus d equals negative 14 plus 32 over 3. And get a common denominator, put those together. So anyone have that one yet? let's see.